So this is exercise 5 text, which you have hopefully all seen and read. There was some interesting issues for the lab sessions that I've visited last week, and also previous weeks for that matter, where I get these, let's just call them stupid questions, where people are asking for permission to do things. It's like, you don't need to ask me for permission to write code. And then we also have interesting questions like, well, interesting scenarios where people just read the text until there's something that they can do and then don't read the rest of the text. And it's not just one group. There's many groups where this happens. Just always read the entire text of an exercise first, and the same thing on the exam as well. Read the entire exam text first before you do anything else, then read it again where you note down what you actually need to do, and then you start actually doing something. I've also seen it when grading exams. I can tell when people haven't read the entire thing, because sometimes you get a hint for the previous stuff and the later stuff, and whatever. Read the entire thing first. So what I'm going to do now, I posed some questions here. Why we consider events first and then state, which was the shell ordering. Why do I switch event first and then switch state, and not the other way around? I'm not sure if I'm actually going to answer this one. And then the second one was, where does the divide goes between these two? And that question I did answer previously today, which was the divide goes between what data needs to be modified. Do you see this now? Well, I'll go through this process. There we go. So I'm going to do the analysis of this state machine from exercise 5, which I want you all to implement, unless you have a very good reason not to. But please talk to me first, and don't just assume you have a good reason, because you probably don't. I'm going to use not this elevator from this project, because it's almost too simple. So I'm going to use the one from TTK4145. For this analysis, just because there's more stuff. It's a bit more complex and more things to handle, which means that the analysis is a bit more interesting than, hey, we have 4 booleans, or we have 2 booleans with 4 possible states, and we end up with 3 of them. It's more interesting to go from 16 down to 6. So it's the standard operation for a single elevator, but we also include the stop button in this one. And note that this is not in this course, it's just here now for making the analysis a bit more interesting. So the specification for how the stop button should work is that when you press the stop button, it should clear all the orders, and it should immediately stop the elevator from moving. And then when it's released, the elevator should remain where it is, even if it is between floors, and then behave like an idle elevator and only resume running once another hole call or a cab call button is pressed. So that's the additional part of the specification. So let's just go through the entire process. First, find inputs. The inputs should be events. Why should the inputs be events? Well, it's the same. It's the ordering the data flow in the same direction as a control flow. Instead of going in and grabbing the inputs, what is the input, and then getting it out, the input happens as an event. And the thing that you achieve by this is that the event only happens when the event happens, but reading the input happens whenever you read the input. So for logging purposes and debugging purposes, it's much easier to have something that happens once instead of something that happens continuously. So that's the primary reason for wanting events instead of just polling inputs. So let's look at what the events should be. Well, button press, possibly also release, floor arrival, the stop button, both press and release, and of course time, because time is always an input. So that's not explicitly in any specification or explicitly connected to any hardware. It's just time is always an input. It's just worth having. And then on the output end, the outputs should always be the end goal of your system. I've seen a lot of shitty elevator algorithms where the output of their algorithm is what is the next floor we should go to. Well, last time I checked, the output that we set to the elevator hardware isn't the floor, it's the direction. So your algorithm should return a direction, not a next floor. Next floor doesn't make any sense. So the shell functions should write to the hardware outputs eventually, and the core functions should figure out what should we write to the hardware output. And the core functions are the algorithms. So let's look at what the outputs are. The motor direction, obviously, not the next floor. The motor direction has 3 possible outputs, up, down, and stop. The door is an output. The floor indicator is an output, which is just what floor are we at as part of that specification. It's not super important, but it's there. And then, of course, the button lights. And yes, finally, the stop button light, because that's also part of this specification. So now we have the inputs and the outputs. We want to figure out what the state is. Well, the state comes from the inputs and the outputs. So that's whatever data needs to be retained from previous iteration to next iteration. And hopefully we don't have all the previous outputs and all the previous inputs, because that's infinite space. We don't like that. Or just the singular previous and singular previous of inputs and outputs. That's still a large space. We probably don't need all of them. So let's see if we can get rid of as many of them as possible. So we want the simplest way to store the least amount of data, and we want functions that manipulate simple representations of data. They're like next floor can always be generated from the direction and the previous floor. That's always going to be the next floor. So we want to have the minimal, simplest representation. You can always, if we need more complex representations, we can always write a function that transforms simple thing into complex thing. But you probably won't need them. And of course, this data comes from the inputs and outputs. Yeah, these are just the core functions. So this is an iterative process, usually. You can say we want everything and eliminate it. That's also an iterative process. Or you can say we think we don't need this thing, so let's see what happens with our analysis if we don't include them and then later include them. But today I'm going to do top-down everything into nothing, or everything into minimal. So this also happens a lot in, especially this elevator project, where they're like, oh, we need more data, let's add more data. And eventually you end up with a state representation that has duplicates of data, it's yucky. So duplication is usually a bad sign, and invalid combinations is also usually a bad sign. So we're going to use we want to remove duplicates and we want to remove invalid combinations as specified in the specification. There are things that don't make sense for our elevator system to be doing. For example, moving with the door open is not something that we want our elevator to do, so it's an invalid combination of state. So I like doing it with Boolean data, because Boolean data lets us create a table and perform some rather mechanical analysis on it. And then we're going to reduce that later. We don't want everything to be Boolean data. Like the floor we are at doesn't need to be Boolean data. It doesn't make a whole lot of sense. But like if a button is pressed or not, if we are moving or not, the direction we are moving in isn't a Boolean. But does the elevator fundamentally behave differently if it's moving up or moving down? Well, it's the same algorithm. It's just 180 degrees flipped. And also, does the elevator fundamentally behave differently if it's moving up from the 3rd floor or moving up from the 2nd floor? Yeah, not really. So there are these, it's not a very rigorous analysis to make claims that direction isn't relevant here and floor isn't relevant here. This is just based on intuition, but that's acceptable. Intuition is an acceptable tool. Use it. So from the inputs, we have which buttons are pressed, yes or no, button has been pressed or not, which is just a 2-dimensional table of Booleans. That's the simplest representation that I could find. I've seen people do lists, chronologically sorted lists of the most previous order that has arrived. It's just a table. Chronologically sorted lists is a much more complex representation because you only have floor versus button type. Yes or no. When isn't relevant, so you don't need the third dimension of time there. What floor we were on previously, that's just an integer. If the stop button has been pressed, that's a Boolean. And then from outputs, if we are moving, which is a Boolean, if we are currently positioned at a floor, being positioned at a floor means that stopping is now a viable thing to do. Once we arrive at a floor, we can stop and open the door. That's also a Boolean. We can, moving and at a floor, it's not like, or we can be stopped between floors, but we can't open the door. So these are two separate Booleans. These are not just three states. These are actually, it's not just stopped at a floor with the door open, stopped at the floor with the door closed, and moving between floors. We can also be stopped between floors with the door closed. So these are, why did I include the door closed? Oh, whatever. You get it. These are 4 unique states, not 3 unique states. Then the direction, which is some custom data type, probably an enumeration. We have in the specification that up and down should behave differently. So we need to include up and down and not just is moving. And then we have the door open or not, which is also just a Boolean. And then what button lights are on, which are probably not even necessary to store because if you push a button, you turn on the light. And when you arrive at a floor, you turn the floor indicator to that one. So these don't need states. So again, just using intuition to find out that these are so simple that we don't need them. Which means that we end up with about 4 Booleans that we want to reduce the space of. So 4 Booleans gives us 16 combinations. And we want to find which of these 16 combinations are not valid combinations based either on the physical reality of the world or from the specification that the elevator system shouldn't behave like that. So these were the 4 Booleans that we remained. Floor wasn't a Boolean. Button lights were just one-to-one mapping. We excluded them. Direction was also not a Boolean, so we removed these. So these are the 6, that's 5, combinations that are invalid. So we draw up the table of just, the top row is 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, and so on, all the way down to 1, 1, 1, 1. And then we eliminate all the rows which have some of these. So moving with the door open, obviously that's not a good thing. The door open when we're between floors, again, obviously not a bad thing. Stop button pressed while moving. We don't need to have it's like, yes, we can press the stop button while we are moving, but we cannot be in a situation, we cannot store a state in our program that the elevator is still moving while the stop button is pressed. So these are state representations, not event plus state representations. So the elevator cannot store a state for next time such that the elevator is moving with the stop button pressed. Does that make sense? Yes? Okay, cool. So when we remove all of these invalid combinations, we're left with only the valid combinations, which are these ones. So we went from 16 possible combinations down to only 6 combinations. So these are the states that remain. Those of you who took this elevator project last year probably recognize most of these. I see one person nodding, so that's cool. So we've collapsed our state space into, I like to call this a behavior space, because the state is all the data that exists, but fundamentally an elevator behaves differently and reacts to events differently when it is moving versus when it has its door open. So I like to think of these more as behaviors, not just state, because state can also mean all kinds of data. But I think the traditional word is just state for this, as in finite state machine state. So we've collapsed the data by removing duplicates. We've removed, well, you can be door open at floor 4, door open at floor 3, door open at floor 1, and so on. So these are essentially duplicate behaviors, so we removed those. We got a final variable, which we gave a unique, nice name, which describes how it behaves. And then we can even do a further collapsing, standing still after an emergency between floors and standing still after we've closed the door at a floor. The elevator behaves the same way to new events in both of these situations. So we can collapse those both down into just a single idle state. So the standstill state is now eliminated, so we're down to 5. Might be beneficial to include more things. In our case, there is one other behavior which might be useful, which is the initial state, which is we are between some floors, but we don't know which floors we are between. So it might be beneficial to add these things. Usually these are just initial states or end states in some cases. For most control systems, there is no end state because the end state is you have died. But in this case, the init state is pretty simple because it has a unique transition to idle the moment we reach a floor. So you initialize the program. If we're not at a floor, you drive downwards until you reach a floor, and then you transition to the idle state. So yeah. So we have some new minimal data. We have a 3x4 array of booleans. We have an integer for the floor. We have an enumeration for the direction, and we have the behavior of the elevator system, or state machine state, as it were. And while I didn't intend to end up with a state machine here, but interestingly enough, I did end up with a state machine here. And that's an important subtlety of this analysis. I didn't go out of my way to introduce a state machine. It just so happened that I ended up with it. So we have our inputs, we have our outputs, we have our minimal representation of internal state. I think you're all familiar with this from either this elevator project or the previous elevator projects. Yes, we've increased to 6 people nodding, so that's good. Okay, so we have this pure function that transforms event plus previous state into next state, and we want to split this one up so that it's not just one giant function, because one giant function is a pain. So we had one giant function that returns the output actions and the next state from the input event and the current state. So we want to split this one up into more maintainable chunks. And then after we've split them up, perhaps we want to group them into some logical grouping. So the first split we do, well, you've already seen this. We only call a function when an event occurs. There's no reason to transform our internal state if nothing has happened. So the logical place to perform the first split is, depending on what has happened to us, call one of a set of functions, which gives us, instead of one giant function, we have one function for each event. Makes sense. Now we can do another split. We can create another sub-function. Because we have this state machine behavior elements, well, we can create a sub-function for each of these state machine states. So we switch on the event depending on what happens, and we switch on the state depending on what state we were in. So now we have these 2 nested switch statements. Of course, we have a combinatorial thing going on here. We have a set of different events, input events, which had 4 input events, and then we had 5 states, 4 times 5, 20 combinations, might be a bit much. And not all of these are valid. Like, we can't arrive at a floor when the door is already open because we're standing still. So that combination, there's nothing to do, and it doesn't make sense for it to occur in the first place. So a lot of these combinations turn out to be no ops or very simple ops. So we need to figure out where exactly does the complexity lie and then implement the functions. The core functions, the pure functions, the algorithm itself, we need to implement those for where the complexity lies. Well, let's figure out where the complexity lies. Well, the complexity lies where we need to modify our own state or modify the output of the system. That's where the complexity lies. That's where the operations lie. But often we don't need to modify the entire data. If you look at this function as it's defined here, the bottom one, event, the function for some event and behavior combination, we're modifying the entire data structure, both the current floor and direction and button table and behavior. Usually we don't need to modify all of these at the same time. We only need to modify one or two. For example, if we get a button press while we're moving, well, we don't need to modify with the direction and the floor. We just need to modify the order table. And similarly, when the door closes, there's a timeout that says the door should close now. Well, we're only changing the direction. We start moving. We don't get a new order because the door closes, and we don't suddenly arrive at a new floor as a result of the door closes, although teleportation would be a nice thing to have. So our focus is now really looking at pure functions that return one piece of data, not pure functions that return the entire new state, because those would be easier to create. So let's look at what these functions should be. Let's see. We have functions that return what the new button table should be, or a function that returns what the new floor indicator should be. Well, these are pretty trivial. The button table should be updated when someone pushes a button. The floor indicator should be updated when somebody arrives, or when we arrive at a floor. So these are so trivial that we don't really need to write a function for them. But this one, the direction one, is a little rougher, because we have multiple sources for where a new direction or a change in direction could be warranted. If we're idle and we push a button, it makes sense that we need to choose a direction and move towards the new order. When the door timer times out and we close the door, it makes sense that we choose a direction and start moving in that direction. And then when we arrive at a floor, it makes sense that our direction might become stop in order to let people off. So this choose direction function has a non-trivial implementation, so it is a function that modifies one piece of data, which is just direction, but it depends on a whole bunch of inputs. Basically all of them, except maybe behavior. So this is a function that we need to create. This is where the majority of the algorithmic complexity lies. But of course, these have three different sources, so maybe we want to split this further and say that there's a separate function for floor arrival, and we call it should stop. So this is based on intuition again. This isn't necessary. You can use the same function for all three of these. It will work fine. But it might make sense to have a separate one for should stop. So, I'm now going to show you how this looks like, which you've probably seen already. But I'm going to do it in, if this thing allows me, I'm going to do it from Golang, because I already have our state machine function implemented in Golang. Is this large enough, or do I need to embiggen? Can I get a hands up for embiggen? No hands. Okay, so this is large enough. Unfortunately, it doesn't use the... So if we could rotate the projector, that would be nice. Okay. So we have our state machine function. And then we have the for select, which is the way a process should always be. Should always be a for select in your Go processes. There's no excuses here. The first level of switching was based on the events. And the events are, we get the events from channels. So our first switch is the select. That is the outermost switching function. And then we have one function for each event that occurs. That is a content of a select case. With me so far? And then within each select case, we have a switch on the current behavior state. That is our second level of shell. And then within these, we can live with a single level of if, but no more. Because now we're 3 levels deep and we don't want to go any deeper, because then we create an untestable and unmaintainable mess. So we've reached our maximum depth now. 3 levels. 1 for the channel, 1 for the switch on our state machine states, and 1 for a single if. So when we're integration testing this, the thing that we need to analyze is that single if on the inside. And I think we can manage with the single if. That's within the scope of our ability to comprehend without any further testing. But within these ifs, we have the core functions. And these core functions, these are the algorithms that decide what the next output should be. They don't actually apply any output. They have no side effects. They do not communicate with the outside world. They do not set anything on the elevator hardware, and they definitely don't read anything from any other modules. These are the pure functions. And you can see some here. Not set motor direction. We have a clear requests function here, which is a bit interesting. And then we have, where is our should stop function? There's our should stop function. This is algorithm. This is just pure input output, returns a Boolean, takes an entire elevator state, and also implicitly, of course, takes the event relevant. So it takes an event, it takes the behavior implicitly, and then explicitly takes the remaining arguments, which is floor, direction, order table, and, well, also has behavior in there. And let's see, where is our choose direction? And here's our choose direction function. Also, pure function. So this is the shell. This state machine is the shell. And there's perhaps more complexity than necessary because I wrote this yalla fast. But the interesting part is the core functions, which are these ones. These are pure functions. We have a 3-level deep nesting here. We have some more nesting here and some, well, requests below and requests above. So I guess this should stop function effectively has, is it 4 or is it 5 levels of nesting? So these are algorithmic functions. And you've already seen these implemented in C, in the elevator algorithm in the project resources repository. So that's why I ended up with this structure, is the core and shell split. As much as possible in the core functions until it doesn't make any sense anymore. And then back to the shell. That didn't work. Back to the shell. As little as possible, but I haven't completely achieved it. I'm not super happy with it. But most of this comes down to a limitation of the language in this case. Because in Go and most other imperative programming languages like C, Java, Python, whatever, it's hard to have a function return a list of functions which are the outputs that should be applied. It's much easier to just return a single value and then you figure out what outputs should be applied. For example, this choose direction thing here. We get a new direction. Yes, references, thank you. But I didn't return, this choose direction function didn't return what the next state should be. Because it's a bit tricky. Well, I could do a multiple return and also return next state as well. But in this case, it's easier just to put that into the shell. So taking a bit of a lazy but pragmatic approach to this. So this is the general structure for, this would have been the general structure for your state machine last year, for those of you who took that course. It is the general structure that I proposed in the C code that I gave you, and it is the structure that I would absolutely recommend that you follow. Maybe not in this detail. There are going to be more states, probably, in your state machine, because there are error situations that you need to handle. But I want to look at now this top part here. this thing, the parameter list for our state machine. These are, well, if you ignore the first one, which is just an initial elevator, which is just an elevator initialized to who knows what, some default values. The rest of the arguments are just channels. That is the shell. These are the inputs of our process and the outputs of our process, which can be connected to whatever. New requests, which is the one at the top, it doesn't really matter. This is the point. It doesn't matter where new requests come from. If our new requests come from our proper order management subsystem that actually does the consistency across multiple systems or acknowledgement procedure or whatever, or if it comes directly from a button press, for the sake of this state machine, it doesn't matter at all. It's just a value that comes from somewhere. Which means that if we want to test our state machine, we do not need to test our order verification acknowledgement consistency system. And in order to test our order system, we don't need to have a state machine that executes the orders, because they are just connected with values over a channel. There are no function calls that we need to mock out. There are no objects that have a bunch of public functions that we need to create proxies for. They're just values. Does that also make sense? So I'm going to conclude now for how your Go program should look like, because there's a lot of you Go programmers. But it also applies to you Erlang and other. Oh, come on. Oh, jeez. There. So for message passing languages, I just want to put up some, let's just call them guidelines as well, perhaps even rules, for what your program should consist of, this core shell split. So your core functions should be pure functions. They should only have inputs and outputs, should have no persistent state, and they should have no side effects. This makes them testable, which you would probably like to do, but possibly not even need to do, which is convenient. And then your shell functions should just be the communication. So they should have as little algorithmic complexity as possible, and as much all the communication that you need between processes. And these have persistent state, and they never return. And then either one process spawns sub-processes, or all your processes are spawned in main, which is the normal way of doing things. You create a bunch of channels and then create a bunch of processes. In this way, well, a tell for your Go program being a bit shit would then be a function that takes both a channel and inputs and also returns a value, or some combination of these. If you have a function that takes channels, it should be spawned as a Go routine. If you have a function that does not take channels, it should only have inputs and outputs and do nothing else, generally speaking. If you just follow those rules blindly, you will almost always end up with a good program. That's kind of just the way it is. And then if you also pay attention to this, putting as much algorithmic complexity as possible into our pure functions while following the split between the two kinds of functions, you will definitely end up with a good program. So that has a happier ending than last time, because this time there are some rules you can follow, some principles you can follow, and you will get a good result. Which is convenient. That's a happier ending than last time.